Started. Thank you.
Thank you. Yes, please ask me any questions that you would like. I'm happy to answer them. Okay, I have received only 2 questions as I can see. By the way, am I audible? Yes. Okay. Yeah, please go ahead, Jahan. Please go ahead and ask a question.
Good afternoon, sir. Sir, am I audible?
Yes, you are. Please go ahead.
Sir, I was trying to solve a problem about MOSFET noise,
Yes.
in which we had an RD, an RS, and a MOSFET in the common source stage.
Sure.
So, sir, one approach which I had seen in Razavi to calculate the contribution of the noise was that they took the current noise across the MOSFET to the input side by dividing it by GM square, and then back to the to its equivalent output voltage by multiplying by the gain square.
Right.
Now, the same problem, I was trying another approach, which is also in the textbook, where they make the current source, because it's across a kind of like a floating node, into 2 current sources with a ground in the middle.
Right.
So, sir, in that approach, we make the output grounded and we see the currents flowing through the output and multiplied by the output resistance square.
Right.
So, sir, in that approach, we are finding the flow of the current from the top one to directly go into the ground output node.
Right.
And the other one is going through the RS and the MOSFET channel.
Right.
So there the current will split based on the ratio of the impedance seen by the source, which is 1 by GM, and the RS.
Right.
So, sir, if I can show, but if I put numbers, basically, then basically one current is going in and the other is coming out at some fraction of it. Assuming the RS is equal to 1 by GM, then that should be like half the current is going to cancel on the output end.
Right.
So, sir, in this approach, the complete current source is not appearing at the output node. But in the other approach, which I had seen in Razavi, they had taken the complete current and divided by the GM and then taken it to the gain. So why both the approaches are giving me a different answer?
Yeah, that I see to find noise, what you have to do is basically find the transfer function from the noise source to the output, and square that transfer function and multiply it by the noise spectral density of the noise source. If you have multiple noise sources, you find the transfer function from each of the noise source to the output and multiply by the square of the transfer function. And you add up the noise spectral densities due to each noise source, because all these noise sources are independent. Okay. Now, after that, it is just a matter of circuit analysis, right? See, the only difference between, whether you refer it to the input or whether you, do it directly is simply are equal. I mean, you'll be basically finding the same transfer function in multiple ways. Okay. So if you get, and whatever method you do, you must always get the same answer. If you don't, that basically means that you're making a mistake somewhere.
So, sir, where you think I'm making the mistake, I'm not yet.
Maybe you can send it to me by email, and then we can do
yes,
that.
sir. I'll write it properly down right now, sir.
Sure.
Thank you, sir.
No problem. So there was a circular. I mean, there was a form circulated, and I only have 2 questions. There was one question by an Arnab. And his question is not really technical, but a general one, which says, as we grow up in our engineering career, concepts become very complex and very mathematical. Is there a way to simplify things? Too much in-depth mathematics suck away the motivation out of people. Well, I mean, the equations are evidently necessary, right? Because we are dealing with numbers and quantities and, way things flow and so on. However, if you think about it deeply enough, you'll be able to find the intuition behind the equations, right? So, and it is that intuition which is important, and that will also help you be able to remember the equations, when you want them to. So this is the approach is it's not only that you should remember the equations, but more importantly, you should understand the intuition behind the equations, and then they will stop being as intimidating as they seem, right? And stop seeming as boring as they seem. Okay, the second question is by one Gurunathan. Let me read the question for you. We know that the field of power electronics, again, this is not related to this course. So in the field of power electronics, there are other devices which are, which are obviously much more efficient in some sense or the other, like silicon carbide and gallium nitride. And of course, so if, the question is, are these devices going to take over the world, or compared to CMOS? And the answer is, well, the reason why CMOS is still there in spite of all sorts of devices is the cost involved in manufacturing them is so small compared to many of these exotic technologies. And the fact that you can integrate analog and digital easily on one die makes for a very, very strong and compelling case to be able to integrate analog, digital, and all that stuff, and RF all on one single chip. Okay, so that is the bottom line, and that's the reason why CMOS is definitely here to stay for a long time to come. Of course, gallium nitride is very advantageous in niche applications. Like one of them is power electronics, as you pointed out. The other one is RF power amplifiers. Basically, you can make very, very efficient, power efficient amplifiers with gallium nitride, and that's basically what. There will obviously be niche applications like the ones you pointed out, which will continue, which will move to gallium nitride. But the main, the most of the processing, when the powers involved are very small, it's hard to beat CMOS. But of course, one never knows, when somebody comes up with something so innovative and compelling and cheap. And when such a device comes along, then it has the potential to replace CMOS. I hope that answers your question. Is there any other question? Yes, please go ahead. Yeah, I'm not sure if there are no further questions, then we can close the session. Okay. Since it appears as if the number of participants is quite small, and we've got no questions either on the forum or on the Google Sheet circulated, or in the or in the chat box now. Or yes, Gurunathan, again, if you have a question, please shoot. Yeah, you can use the audio. You can speak. Or you can share the screen also if you want to.
Sir, I think he is not audible to us. It is showing unmuted for.
Let me. Oh, sorry. No, but Gurunathan, no, he's unmuted. It is unmuted.
Sir, but it is not audible to us. Maybe.
Not sure what's happening. Or you can type it in the chat box then, I suppose. Okay, so while he's typing the question, I'd like to, since we have very few people here, I'd like to ask people one by one. Which topic in the course did you find the most difficult? You can type the answer in the chat box. These kinds of things are useful feedback. So Abhijit, what can you in the chat box? Can you type Which topic you thought was the most difficult to understand in the class? Hi, Abhijit. Oh, well, how to prepare for the TIMS program? Well, I think you should be very thorough with the basic, with basic circuit analysis, like at the level of electric circuits and networks. So we expect you to know, have intuitive feel for analyzing and understanding networks, transfer functions, and so on, and basic knowledge of analog electronics at the level of this textbook. Okay, stability of negative feedback was the hardest to understand. Yes, I think I can kind of sympathize with your observation. Yes, it is a difficult topic. I'm not sure if so, Gurunathan, have you actually done a control system class before, or is this your first introduction to stability and feedback control? Okay, all right. All right. It seems there seem to be no more questions, and I think we can close the session. Thank you all for attending.